So if we have a set D that contains a certain point C, and we have that the function f in that point C is bigger than f of x for every x around that point, then we have that f of c is going to be an absolute maximum on that region D. On the other hand, if f of c is smaller than all the other values in that area, then we say that it's an absolute minimum. Okay? An absolute extreme in general is going to be either an absolute value or an absolute minimum. Now, so that's difficult to picture just from the point of view of the definition. So to give you a more graphical idea, imagine that you're taking a hike in terrain that is changing, and you're going from west to east. Okay, the elevation is going to change as you walk over the hills. Okay, and you go through valleys and plains, and you're gonna reach several high and low points along the journey. So that's gonna look somewhat like this. Okay, so you go along this, and notice that you have certain high points, you have certain like this and this, and you have certain low points like this and this. Okay, if we define a small region around, those will be maximums and minimums. Notice that if we let's take just this piece. This point is the maximum elevation that we have around that area. Okay, so we can define that as the absolute maximum of that area. Okay, now if we enlarge the whole domain, like over here, notice we're translating this curve to the xy axis, and now in here we have a maximum here, and over here it seems like we have a maximum. Over here we have another one. Over here we have another one. Over here we have another one. And minimums, we also have many. We have this. We might have this. We might have this, this, and this, depending on where we're located. So depending on the area that we select our domain, then we're going to have a maximum of that area. So if the area is just this, the maximum is this. But if it's the whole domain, if it's this whole thing, then clearly the absolute maximum is this. In the same fashion, we have this is a minimum, this is a minimum, this is a minimum, this is a minimum. But if I take everything, then the minimum should be this, which is the smallest of all the possible values. Now, when you examine a function over an interval in the xy axis, the values are increasing and decreasing, right? We reach high points and low points. And what we're going to do on this section and in this chapter is to study how functions behave in that way. Now, the existence and location of absolute extreme values depend both on the function and the interval that we're interested. Of course, that means the region that we're trying to take. Notice that if the interval of interest is not closed, then a function might not necessarily attain an absolute extreme. So just as an example, consider this function. We have 4 minus x squared in the whole real line. And what happens here is that we clearly have an absolute maximum here at 0. And that absolute maximum is 4. But we're not going to have any absolute minimum because this function, it keeps going down and down and down, and I don't know when it's going to stop or if it ever is going to stop. So there's no absolute minimum. Now, if the interval is closed, the situation is different. Notice that if I close the interval, I have now 4 minus x squared from 0 to 2. Then I have an absolute maximum at 0, which is still 4. But now I do have an absolute minimum because in 2, we have the 0 value. Okay? So it's very important to ask yourself, do we have an open interval for my region or do we have a closed interval in my region? Depending on that, the existence of a maximum or minimum is going to be guaranteed or not. Now, notice that if I open just one of the pieces, also I can have situations where I don't have the absolute maximum. Notice I just opened the 0 here, so now I'm not taking this value, and so I have no absolute no absolute maximum here, although I still have the absolute minimum. But also I can have the situation where I have nothing, even if it looks like I should. But if I open the 0 and the 2, notice that I'm not going to have any absolute maximum or absolute minimum here. Now, defining a function in a closed interval is not going to be enough to guarantee the existence of absolute stream values. Okay, so for example, notice if I have here, this function is going to be defined in 0 to 1 close in the stream, close in 0, close in 1. But notice that because of the definition of the function, since 0 at the end, I'm getting close to a maximum here, but it's never reached. And then it goes down. I do have an absolute minimum of 0, but I don't have an absolute maximum. I can play around with the function in the same way, so you never really attach a number. And notice that even if I'm getting closer, this is like a limit thing. Here, for more that I want to say the maximum is this number, I can't. Because I don't have the image of 1, but can I get closer with 0.9, 0.99, 0.9999? I can never get close enough to reach a maximum. Now, another situations that might occur is like this. And in this case, I also have a possible maximum that was occurring here, but because I have a hole in there, then it's not really occurring. Notice that this could potentially be going towards a maximum, but since there are higher values over here, then it isn't really going to be reached. So we don't have a maximum volume here. We do have an absolute minimum. This is the possible absolute minimum in this closed interval. And that's it. So the discontinuities are really, really, really bad to get me absolute maximums and absolute minimums. Now, so let's find a way to define when we can have that, which is the closed interval. So for that, we have the stream value theorem. And the stream value theorem says that a function that is continuous on the closed interval AB has an absolute maximum and an absolute minimum of that interval. Okay? So if the function is continuous and the interval is closed, if we have both things, then we can guarantee that we have both maximum and minimum. So let's take a look at some more examples. So for the functions in here, we identify that the location of the absolute maximum value and the absolute minimum value on the interval AB. Notice clearly here the minimum is C. This is the absolute minimum. And the absolute maximum is going to be the image of A. So here we have f of C, here we have f of A. F of A maximum, f of C minimum. F of B is not going to be anything in particular. Now this function is continuous, it's in a closed interval, and therefore this satisfies the stream value theorem. Now in this case, we don't have the stream value theorem. Notice that we do have the function defined in a close in an interval, but the interval is not closed because the streams are open, and we have discontinuity here. So we don't have any guarantees from the theorem. However, you can see clearly that this function does have an absolute maximum. This is the maximum here. Okay. Now, does it have a minimum? No, it doesn't. Okay. And it's not guaranteed because we don't have the stream value theorem in here. This function is not continuous. The interval is not closed. Now, for the following function, let's see what happens in the interval AB. So first, we can have a couple situations that happens. So over here in P, we're going to have a local minimum. Notice that now that we can talk about different areas to check minimums, then instead of necessarily talking about the full domain, we can say, well, this point is going to be a minimum locally. And so you can see that this point is a minimum locally. R is another minimum locally. Okay, but it's not the absolute minimum. The actual absolute minimum is going to be f of b, because this value is lower than any of these peaks that will be normally a minimum. Now, in terms of maximums, notice that potentially this q is a local maximum, right? Also we have that the value in s is a local maximum, and when compared with the other values, we see that this is the biggest, so that's going to be the absolute maximum. Okay, so now we can get an idea that the absolute maximum is the greatest value among all the local maximums as well. Now, the definition for this would be, suppose that you have that C is going to be an interior point of some interval. Okay? So if you have that the image of that point C is bigger than all the functions in that interval, then you have a local maximum. And if the image of that f of C is smaller than all f of x in that interval, then it's a local minimum. And you can see that here. So this is a local minimum. This is a local minimum. They're the smallest value in a given area. So for example, from A to P, this is a minimum going on in all that area. From Q to S, this R value is again a local minimum. This is smaller than all the other values of the function. Okay, and so that's what this definition is saying. For something to be a maximum, the value of the function must be bigger than all the values around. For something to be a minimum, then the value of the function in that point must be smaller than all the other values around. Now let's check another example. In the following figures, it shows the graph of a function defined in the interval AB. Let's identify the location of the maximums and minimums using the terms absolute and local. Okay, so first, clearly we can see that this point P can be a local minimum. Also, the point R can be a local minimum. And that's it. Those are the points where we can reach a local minimum. Now, this point in P is going to be the smallest of all the values in all the domain. So that's going to be the absolute minimum. Okay. Now, in terms of maximums, notice that Q is a maximum, S is a maximum, but they're both at the same height. Okay. So can we really talk about having a maximum, an absolute maximum? No, I don't think. We can only talk about local maximums with Q and X. Now, let's talk about a little bit about what's happening when we reach a local maximum and a local minimum with in terms of slopes. Since we want to talk about the derivative and make interpretations with the derivative, let's see what happens. Notice that when we're reaching a summit of some sorts, like a maximum, then the slopes of the tangent line are initially coming in positive, and then when they reach the point, they become flat. So the slopes of the tangent line, they become a 0, and then the slope of the tangent line becomes negatives when we go after the maximum. So in terms of secant lines, we can also think in that way. The secant lines here are going to have positive slopes, and the secant lines from these sides are going to have negative slopes. And that's one way of defining when we have local maximum. With this, we can infer that the same thing is going to happen with the minimum. So we're going to have a flat situation on the maximum or minimum value. And so if f has a local maximum or local minimum at the value of c, and f prime of c exists, then f prime of c is going to be 0. What this means is, in that point c, if c is a maximum or c is a minimum, then we have a flat slope.